Recording in progress.
Hello.
Hello,
Good evening.
Prof.
How are you doing, Glory?
I'm fine, Prof. How was your conference?
It went really well. It went really well. We're doing a lot of trying to make a on-ramp for minorities to go into biotech. So we were in Boston meeting with all the big pharmaceutical companies and having a nice summit to talk about what are the best ways to get students into jobs like that. You know, like in
Welcome back.
biotech, in the pharmaceutical, doing research like that.
That's a good work. Welcome back.
Well,
Must have
stuff that
been
you're going to be
impressed.
eligible for.
That would be great.
Yeah.
Let's see, battling with calculation here. I've been going through it again and again. It's the conversion part that I need to grab at my fingertips. That is it. So it's going well.
How have the power issues and connectivity issues been where you're at now?
Well, I'm now in AU, so power issue is no more a problem.
Okay,
I
good.
think we are fine. Yes. It's only on Monday I arrived, so the connectivity, I didn't get wide connected to the school Wi-Fi, so I'm okay now. It's fine.
How are you following along with the class?
Yes, I've been playing all the videos up and down. But presently, I actually finished the last one, so I'm getting on well. We just need more practice for the conversion. So the formulas are at hand. And just a little conversion so that I get at the right answer. Yes, it's fine.
Good. Hi, Keldrin. How are you?
I'm good, and you?
Doing good. I'm just gonna send out the invite link just in case. Sorry, a lot of folks here. Okay, great. Why don't we go ahead and get started, because I don't know how long it's going to take for others to get here. First thing I want to do is, why don't we just start out with a quick little quiz, just because I want to see where your heads are at. Let's see. So if you go to the chat, go ahead and paste in a link to just a short quiz. Should take about 4 minutes, not even. So it's just about, when we started talking about atmospheric composition, what are the 3 main gases in the atmosphere? If you can, remember their relative percentages. And if you're close in the ballpark, I'll give points, that's fine. The 4th question is how much carbon dioxide is in the atmosphere? And then lastly, what in our atmosphere has the greatest impact on the greenhouse effect of the atmosphere?
Yeah.
I hear birds chirping. That's so nice to hear. Are you able to enter it into the link, Glory?
No, Prof.
Okay. And yeah, you can just paste them there. Send them directly to me,
Okay.
I think, instead of sending to everyone.
Okay. The second question, Prof, send the first one.
Yes, I got it. Good.
The second question
Is what are their relative percentages?
okay.
Okay, and then the last two questions, how much carbon dioxide is in the atmosphere and what in our atmosphere has the greatest impact on the greenhouse effect? If you could go ahead and send those responses in. You know, I do these quizzes less as a grade than to get you to try and think about it and remember what we talked about, because it kind of fits in what we're going to talk about next year. So why don't I go ahead and share my screen? Okay. Go ahead and hit send on your whatever you got done so far. Only got one response in, so yeah, send that in. And let's see. There we go. Okay. Good. So what are the four main gases in our atmosphere? Or I'm sorry, three main gases in our atmosphere. It would be nitrogen by far is the largest percentage. I'd asked for three in the question. That's fine. I threw in water vapor here for this, and treating it as a gas. But nitrogen by far is the largest, about 78%. Oxygen is the next biggest component, and then there's a little bit of argon. Now, water vapor can make up anywhere between 0.2% and 4%. Does anybody remember what parts of the globe tend to have more water vapor than other parts of the globe?
Is it both the northern and southern poles?
It's northern hemisphere versus southern, which has more, well, not so much southern. So for water vapor, it's not evenly distributed. On the polar regions, you'll have really low percentages of water vapor, and in the tropical regions, a lot more. So warmer air can hold more water vapor. And so if the air is really cold, that water vapor precipitates out. That's why we get rain and snow. Cold air hits some warm air, it cools the air down. That air can no longer hold as much moisture in the form of water vapor, and so that condenses into the form of rain or snow and then falls. And so wherever it's really cold, you're not going to have that much water vapor. Wherever it's really warm, you're going to have a lot more water vapor, up to 4%, which, you know, is more than the amount of argon, right? It's in the atmosphere. It can be quite substantial. Now, one of the questions I had asked was, well, okay, I guess I had asked about carbon dioxide. And so the answer for that was about 410 ppm. That's a number you should know. You should have a general kind of idea in terms of, you know, what is the current concentration of carbon dioxide in the atmosphere. And that's at about 410 ppm. So the last question I had asked is, what's the biggest contributor in our atmosphere to the greenhouse effect?
Oh, I didn't get that.
Caldron, you got that? Or Shepard or Zach? That's Q. What's the biggest contributor to greenhouse effect in our atmosphere? First off, does nitrogen, oxygen, or argon contribute at all?
It will be oxygen. And my answer was the amount of oxygen within the atmosphere, but I wasn't sure if that was correct.
That is not correct. Actually, the biggest effect in terms of greenhouse gas is, anybody know? It's not carbon dioxide. No, it's carbon dioxide is important. That's the one that's man-made that we have the biggest control over. But actually, the one that has the biggest influence is water vapor. Water vapor actually can do a lot of screening, and we'll see why that's the case in a minute. But so this business of water vapor is really, really important, because remember, if the air is warm, it can hold more water vapor, right? Well, what's happening to the temperature of our planet? It's warming, which means the air is going to be able to increase the amount of water vapor it can hold, which will then make it warm faster, right? So there's this kind of synergistic snowball effect, or the reverse of a snowball, if you would. And so it really gets down to, what is a greenhouse gas? And how would you define a greenhouse gas?
A greenhouse gas, I would find it as a form of gas that's derived from the earth, with a combination of with a combination of human influences that essentially warms the entire globe.
That's a neat definition. Certainly it applies to carbon dioxide, but we don't want to skew our science by defining it as human caused, right? So we want to take just a general kind of physics view of what a greenhouse gas is. And the easiest way to think about it, you all already actually know the answer to this, because think back to our climate models. When we did a climate model with a planet with no atmosphere, and then we did a climate model with a planet with one atmosphere. What was the key feature of that atmosphere that made the planet warmer? Remember, we saw a temperature rise when we put on a one-layer atmosphere. We got more of a temperature rise when we put on a two-layer atmosphere. And we saw that that would keep going up if you add more layers of atmosphere. But what was it about the atmosphere that made it heat up the surface of the planet?
The sun.
Think of those lines
The
you were
sun.
drawing. You have a line coming from the sun to the surface of the planet, right? Where's the next line go?
With each atmosphere, it would of course it would
It's
it would hold a certain amount of energy, and thus project both that form of energy to the next atmosphere above and below. And so with consecutive atmospheres, the temperature would in a way be doubled.
Right. So when the light was coming from the sun down to the earth, it wasn't absorbed in the atmosphere, right? It went all the way to the surface. The atmosphere didn't seem to do anything about it. Why is that? Remember when our stuff from the sun was coming down, it went right through the atmosphere, right? And then when we drew our second, we have a line coming up from the surface going into our layer of atmosphere. And I'm going to make this line red. And I'm going to go ahead and put in our atmosphere. This will be our atmosphere right here. This jog kind of your memory of what we were doing before.
Yes.
So notice that this light comes right through the atmosphere. It doesn't get absorbed here, but this light does. What's the difference between these two lights? The light coming down and the light coming off the surface.
The light coming from the surface of the earth is a reflection of the light that's being emitted from the sun.
It's not quite a reflection.
The infrared is absorbed in the atmosphere.
Yeah, it's infrared. Why is the light, so the light coming from the sun, is that an infrared? The light that comes from the sun, is that infrared?
There is.
So from our sun, we're in the visible light spectrum, right? This is all visible light, right? And so our atmosphere, this atmosphere here, doesn't absorb in the visible range, okay? Now, if what Caldrian is saying just on the surface of it, if it was just a simple act of reflection, where this light is, where this light is just reflecting up, it would still be visible light and it would pass right through our atmosphere. Why is the light coming off the surface infrared? Right, this is in our visible spectrum. We know that's between 0.35 and 0.75 microns. Remember, the Earth is acting like a black body. So the sunlight, the photons hit the Earth. The Earth absorbs that energy. Those molecules start moving more because they have more energy. And remember, kinetic energy of molecules, that's the same thing as temperature. So the temperature increases, right? And we learn that when molecules move, because they have electrons, in their outer shells, when you move electrons, they create a little magnetic field. And when that wobbles, they'll shoot out photons. And so we call that black body radiation. And we could calculate using Wien's law what frequency of light would be emitted. Well, in the temperature ranges that we're at right now, all of those black body light that's being emitted would be in the infrared range. We'd have to be up between around 5,000 degrees Celsius or Kelvin before we actually started glowing in the visible light. We're not that hot, right? We're hot enough that the photons being emitted from black body radiation are in the infrared. Well, what makes this a greenhouse gas is that if it's a greenhouse gas, that means it absorbs some of that infrared radiation, and that causes it to heat up. So now it will emit as a black body in both directions. And this was how we worked our climate models, right? We put a number for the solar constant here. We said that to figure out the equilibrium temperature, the amount coming in would have to equal the amount coming out. So whatever number you had for the solar constant there, you'd have there. And we said that these two had to emit the same amounts. And so we could calculate the amount coming in and the amount coming in to the Earth, and that would equal the amount going out. Okay, and so we calculate that. But what makes this a greenhouse gas is it's a gas that absorbs infrared energy. Okay, and instead of letting that energy go out to space, it absorbs it and heats up and then emits it as a black body, like all things do. Remember, black body radiation is something that everything does. Any molecule that's got electrons around it is going to do black body radiation. And that's all the elements that we've got. They all have protons and electrons. So we're radiating in the infrared. So a greenhouse gas would be a gas that absorbs that infrared energy. And this is what, remember, without the atmosphere, we just had heating and then cooling. But because we have an atmosphere, the cooling would go out to space. So those two numbers were equal. But because we have this atmosphere, it gets absorbed here and re-radiated in both directions. And so because sunback is coming back to Earth, Earth is warming up. The surface is warming back up. And so what makes it a greenhouse gas is that it absorbs infrared, doesn't let it go all the way. Just like a greenhouse, it lets some of the energy in, but it doesn't let it all back out. And so the greenhouse gets warmer and warmer and warmer because something's stopping the energy from getting out. Okay, so that bears the question now, since everybody keeps bringing up CO2, why is CO2 a greenhouse gas? And it just goes along with that definition. It's a greenhouse gas because it absorbs infrared energy and doesn't let the infrared energy go out to space. The same would be true of water vapor or anything you want to call a greenhouse gas. Now, in the case of our three big components, remember our three components of our atmosphere, the biggest ones, nitrogen, oxygen, and argon, these are all transparent to infrared radiation. So the infrared could just keep going out as if we didn't have an atmosphere, and the atmosphere wouldn't warm us at all. Okay, now water vapor, that's a different story. We talked about how water vapor actually is a really, really important greenhouse gas. And we also started talking about the CO2, right? It's the next biggest abundance in our atmosphere. And so why is CO2 a greenhouse gas? Because it absorbs this infrared energy. And so now the question would be, why does CO2 absorb in the infrared and like oxygen and nitrogen don't? Like I had mentioned before that oxygen, nitrogen, and argon don't absorb in the infrared. But for a lot of you, that's not easy to remember. I mean, it's just a fact in there. But I think by understanding why, it will be a lot more obvious to you and easier to remember. So as to why CO2 absorbs in the infrared, it's because the frequency its atoms and bonds allows it to stretch and bend. So the CO2 molecule looks like this. It's got two oxygens and one carbon. Each oxygen is joined by a double bond. Okay, so it's got two bonds to the carbon on that side and two bonds to the other. So it's this linear molecule. Okay, so they're joined by these double bonds. Double bonds and single bonds, any bond between two atoms has a signature strength. If you bonded some carbon to, say, a nitrogen, that bond would be at a certain strength and vibrate in a certain way. Bonded to a different atom, like another carbon or an oxygen or a hydrogen, each one would have its own particular strength to that bond, and that bond would wobble at a particular frequency. So the strength of these bonds and the positions of the atoms determines how much and in which direction these bonds can stretch and bend. And so to give you an idea, at this little picture here, here's our carbon molecule in the center, here's our oxygen molecules on the side, and you can imagine those going in and out. That could be one form of stretching and squeezing of these bonds. You can imagine that the atoms also wiggle up and down, or the whole thing moves. Maybe this guy moves a little bit this way while the other two are moving in a different direction. And so you have all these. I'm going to go ahead and let me do this. Let me go ahead. Okay, hold on, let me check for a second here. Sorry about this. Come on, Mr. Play. So these are different ways. So here's the carbon in the center, the two oxygen. And this is what atoms do. This is what molecules do. Their atoms are moving around, jostling and stretching. You can see the bending here of this third in plane bending. They can bend back and forth like this. And if you think of these in 3 dimensions, this thing can be bending as well, up and down. Each one of these is happening at a certain particular frequency, how fast it's stretching and bending. And if you were to play, well, not sound, but light at that frequency, it would make it move faster. It's like its resonant frequency. Sorry, okay, go, back, okay. Slide. Second, come on. Technical difficulty here. Stop this. Okay. Hold on a second. There we go. Okay, so we're back to this. And that's far away where we don't want to be. Okay. So does everybody get the idea that these molecules bend and stretch? Okay. That bending and stretching is going to happen at a particular frequency. Okay. So these molecules stretch and bend at those frequencies. Now we can actually do, we've actually done spectrum analysis of these things to see what are the specific frequencies that those carbon-oxygen bonds vibrate at. And this is an absorption spectra from 1 to 6 microns, showing where these things vibrate. And wherever something vibrates at, that means any waves coming in that are exactly that frequency or that wavelength will will resonate with the molecule and make them move more. In other words, they can absorb energy if it's exactly at that wavelength. And so if we look at these different wavelengths for carbon dioxide, we see that they're in a range within the 1 to 6 micron range. There's a few places where the vibrations are in that frequency range. If we look at slightly expanded and go all the way out to 30 microns, we can see that there's actually a big peak between 15 and 19 microns, where And this frequency range, CO2 molecules can absorb that energy and vibrate. Now, if we look at water vapor has a spectrum that also has a number of these vibrational modes that have a frequency, a resonant frequency in the 1 to 30 micrometer range. And why is that important? Well, this is the infrared range. Remember, our visible light was between 0.38 and about 0.75, right? That was our visible range. So that's down here. CO2 does not have any absorption lines down in this range. It just has absorption lines over here. It's resonant frequencies. If you compare it to all the other stuff in the atmosphere, so here's our water vapor, and this is going all the way down. In this graph, we're going all the way down to visible light range. So the visible light range is between 0.38 and 0.75, right? That's our visible range. And you can see carbon dioxide doesn't have any absorption in that area, but it does in the infrared, as does water vapor, right? Oxygen does not. You can see very few peaks. There's a little peak here, and that's actually an ozone peak. Methane has some peaks. Nitrogen oxides have some peaks, but argon has 0 peaks in this region, and oxygen has 0 peaks in this region. This is showing you the ozone. And so that's why our CO2 is a greenhouse gas, because it absorbs in the infrared, whereas the rest of the atmosphere doesn't. Okay. And because it absorbs in the infrared, that means it's gaining energy from photons that are at those wavelengths, which is going to cause those molecules to bend and stretch more. So they're going to start moving around. When you play that particular frequency, that particular wavelength, it will absorb that energy, and those atoms will even do more of the same vibration that that resonant frequency is at. And what we know about temperature is it's kinetic energy, right? And so if it's moving faster and faster, if the molecule is vibrating faster and faster, that's the same thing as higher temperature, because temperature is defined as the average kinetic energy of the molecules and atoms of the object you're talking about, or the gas that you're talking about. And so they're moving around faster, they're higher temperature. And that's the basis of why carbon dioxide is a greenhouse gas, because the vibrations that the atoms make, those specific atoms between carbon double bonded to oxygen, happens to absorb in the infrared. Carbon hydrogen bonds, they have a different resonant frequency that doesn't happen to be in the infrared, etc. So it depends on which bonds you have. Carbon dioxide just happens to be very photoactive in this region. And since they can absorb energy at those frequencies, they get higher kinetic energy, which means they become at a higher temperature, which means their black body radiation is going to increase, right? Because we know black body radiation is just a function of temperature. You can, if you know the temperature, you can calculate using Stefan Boltzmann just how much power is coming out, right? And you can use Wien's displacement to figure out, based on its temperature, what its peak wavelength is that it's coming out at. So you can tell kind of the wavelength range. But from temperature, you get all these things because they all act as a black body. Okay. So by absorbing at those energies and those frequencies and becoming a higher temperature, they're going to emit black body radiation, which is where we get those two lines, the one going up into space and then the one coming down back to the surface of the planet. like when we were doing our climate modeling. So our climate modeling was all based on these three assumptions: that the atmosphere is transparent to visible photons, they can pass through and not get absorbed, they go all the way to the surface, and none of the gases that we have in our atmosphere absorb in the visible range. So the light comes all the way down. It's probably why we evolved to be in the visible range. Our visible range evolved this way to find the frequencies of light that the atmosphere isn't absorbing in, so we can see really far. If we saw in a set of frequencies where stuff in the atmosphere blocked it, we wouldn't be able to see as far, because not as much of the light would get to us. And even if we had a flashlight in that range, it wouldn't shine very far because it would keep getting absorbed by the atmosphere. So visible light would probably evolved to see in that range, because that's the range that the atmosphere is completely transparent to it. Now, we don't see in the infrared, but we've seen that some of the components, namely water vapor and CO2, and I think methane we listed in there, can absorb in that infrared range. And our third assumption about the atmosphere, this assumption page, by the way, is taken from the lecture on how to build a climate model, is that once that atmosphere absorbs the infrared photons, it will behave like a black body and emit based on its temperature. And it goes both up and both down. And so after learning about the actual, this is before we even discussed what the components were of the atmosphere. But now we've talked about what the components are and take a look at them. And so do you think all these remain true about the atmosphere now that we've discussed all the components of the atmosphere? And do you have any questions about the components of the atmosphere or greenhouse gas effect or any of that? You're all quiet. Should that scare me?
No.
So I want each one of you to give me, on a scale from 1 to 10, which is 10, everything's great, raring to go to the next thing. 1 is, oh my God, I am so lost. Where are you at, Caldrian?
I'm about at a 7.
Okay,
Looking at the
Shepherd?
different points. Yeah. I believe point 3 remains true. Point 2 does not. And point 1 remains true.
Okay. You're struggling with point 2?
Hmm.
Okay. Shepherd, what about you? Where are you at on a 1 to 10 scale? And what questions do you have?
Yeah, Prof. Yeah, everything is moving on well, but where I have a small challenge on the. You say the carbon dioxide is the. Is it the only? Is it the only? Is what can I? Is it the only? What I want to say is it's actually is it the only greenhouse gas? What about the methane, nitrous oxide, and water vapor?
Okay, so we'll go back here. That's a great question. So we'll go back to this slide here. So water vapor is definitely a greenhouse gas. That one, we saw the spectrum of the water vapor and how that does. And yes, so methane and nitrous oxide, they have lower abundance in the atmosphere, 1.8 ppm and 0.32 ppm. But both of those do have a greenhouse effect, as does ozone, which is much smaller amount, and that's much higher in the atmosphere. And another one we didn't talk about were halogens. So these are like chlorofluorocarbons. These aren't naturally occurring. These are gases that, were in hairspray. And when you spray hairspray, some of these gases start to float up and they keep floating up. Those also absorb in the infrared and re-radiate because of black body radiation. So you're absolutely correct. Carbon dioxide is not the only one. We tend to focus on it a lot because of its abundance and the fact that we're putting in a ton into the atmosphere. Methane is still important. It probably actually per molecule absorbs more, but it's 400 times less in terms of its concentration. And nitrous oxide does to a certain extent. Does that answer your question, Shepard? In terms of the other one?
It's answering, but I think in your notes there's somewhere where it's carbon dioxide is the only.
You're right. Carbon dioxide is not the only one. And remember, water vapor actually has a bigger effect than carbon dioxide does because it makes up a much higher percentage of our atmosphere in tropical regions, right? Any gas that's going to absorb in the infrared range is going to be a greenhouse gas. If it absorbs the light coming off the planet, it's going to be a greenhouse gas. And so that does apply to all these other gases. CO2 happens to be one of them, but it happens to be one, and we'll see this in a later lecture when we're looking at the human impact on our atmosphere. We're going to see where we're impacting carbon dioxide the most, which is why I focus on it. But certainly, looking at this spectrum, you can see water vapor is actually the biggest component, but we don't really have much of control over the water vapor. We're not releasing water vapor into the air. That's coming from the oceans evaporating based on the temperature of the planet. Now, as the temperature goes up, there'll be more water vapor in the air, so we'll get a larger greenhouse effect from it because it will be able to absorb more energy and thus heat up more. Glory, how about you? What number are you at, and what questions do you have?
Prof, I think the explanation is okay. You can see that the water vapor and the carbon dioxide CO2 are the major cause of the greenhouse. They are the major greenhouse gases. And I've been thinking that NO2 also have effects, but now I think I'm convinced that it has little impact on the greenhouse. It has little impact. So I was actually surprised to see water vapor. I thought I was carrying CO2 as the major gas that has the impact.
Right,
But
that's the one that gets all the press, right? That and methane a bit. But it's the one I think we don't want to admit the most because we have no control over it.
Yes.
But it's important when understanding the science behind climate change that you get to know the facts, right? So, Zakiu, what number would you be at, and what questions do you have? Zakiu? How are you doing? Are you on a 1 to 10 scale? What are you at? I can't hear you because your microphone is muted. Okay, well, we will go on. I'll check back with Zach shortly. So these are our assumptions about the atmosphere. Those are important in our climate models. And just remember that anything that absorbs in the infrared is going to be a greenhouse gas, because the infrared is how our planet cools off. It should be shooting that light out into space. And if it doesn't shoot it out into space, if it gets absorbed by some molecules, those molecules, since by definition they're absorbing energy, will move faster. Their temperature is higher. They will black body radiate even more, which means not just out into space, but back onto the surface, and that heats us up more. That's our climate change effect. That's the physics behind it. Now, since CO2 is something that we could go on and focus just on water vapor. We can do a whole chapter or chapters on looking at water vapor because it has the biggest impact on the greenhouse effect, but there's not much we can do about water vapor because it's just, it has to do with evaporation off the oceans. Since the next biggest component is the CO2, remember 410 ppm, the reason I gave you that quiz is because I want you to remember that 410 ppm parts per million for carbon. We'll look at the carbon cycles. How does the CO2 get in the atmosphere? How is it removed from the atmosphere? And basically the carbon cycles are the processes which regulate the amount of CO2 in the atmosphere. And there's a bunch of different components to the carbon cycle. There's land and atmosphere interactions. There's also land, atmosphere, and ocean interactions. And then finally, even the rocks play a role. And that you may not have heard about and be kind of surprised at how much rocks play a role in the carbon cycle. So what I'm showing you here, this is a graph. It's a 2-year time frame that's looking at the amount of CO2 in the atmosphere. And this is by month. So September, October, November, December, January, February, March. That's what these letters are on the bottom. So you can see the months. And what do you notice about this graph of carbon dioxide over this 2-year period?
It has
Yes.
peaks and valleys, and it fluctuates on a year-to-year basis.
Yeah. Yes, and you'll see this over and over again. This is a common thing in the spring and the summer in the northern hemisphere.
Okay.
You're going to see that the amount of CO2 goes down. That's the spring and the summer here, right? Here's March, June, July, August, September. And in the winter, in the fall and the winter, you're going to see it start going up.
Okay.
So why do you think that's happening?
Is it due to during the colder months, heat is being, I know it maybe at different factories and plants, heat is being produced to keep and this is just and this is just a wild thought. Could it be at different plants and facilities during colder months they're generating heat a lot more to keep machinery, I guess I would say, working optimally. And in homes, people are of course using heaters and things of that nature to keep a house warm.
Now, this isn't temperature. Look at our scale here. This is the amount of carbon dioxide in the atmosphere. It's going up in the fall and winter, and it's going down in the summer and spring. And so you're thinking of the human effect. And I imagine if we had fine grain, we could see that. But what if I told you in the 1700s, you would see the same fluctuation? I agree with what the fluctuations that you've identified, but those would be the tiniest component in here. Shepard, your thoughts?
Prof, is it not because of trees? Something associated to, let's say, in winter they lose the leaves. Because the trees they absorb CO2. I don't know.
Right.
I think something like.
water,
So
vapor.
when are plants using the most CO2? When are they absorbing the most CO2? What time of the year?
During the summer and spring.
Yeah, summer and the spring. That's where they grow, right? And when they're growing, they're using up CO2. So spring and summer, you using up a lot of CO2. So the amount of CO2 is drastically decreasing. Now in fall and winter, that photosynthesis, a lot of plants go dormant. And so that photosynthesis essentially slows down greatly. And then some other processes contribute. But let's just focus on photosynthesis real quick. We've got, well, maybe we should stop here because we're at 11:50. So what we're first going to talk about is the role of photosynthesis and respiration in the carbon cycle, because it actually has a huge effect on the amount of CO2 in our atmosphere, because it changes from season to season. And we'll pick up on Monday with these carbon cycles. The other thing I would like to share with you before we go is, so you should be finishing or near completing your peer teaching on black body radiation. And so remember, there is a question, a prompt for black body radiation. I've only gotten just a couple, but here is our prompt, just so you can see. Please make a 5-minute video explaining what black body radiation is, what causes it, how you determine the peak wavelength of radiation. Remember, that's Wien's law. And then how do you determine how much power is emitted? There's Stefan Boltzmann. In your explanation, use as an example a cube of 1 meter length that's 150 degrees Celsius. So you'll probably have to do conversions to Kelvin. And since, if you want to pick out total power, you're probably going to need to figure out the surface area of the cube. What is the peak wavelength emitted by the cube? That's your Wien's law. How much total power is emitted by the cube? That's Stefan Boltzmann times its surface area. And then the question is, can you see it glow? In your video, explain how you calculate those values. You do not need to derive any equations, but you should show and use them. So you'll do that. And that one's due now. So we really should be having that one done. And I'm assigning today a new one, basic climate modeling, which I'd like to be done in a week. And in this one, you're going to do one of those climate models. Okay, I want you to walk us through a climate calculation for this planet Krypton. And I give you a solar constant for that planet. And I give you its albedo. And it's got a 2-layer atmosphere. And you can assume that the gas is absorbed in the infrared. So it's going to work like, we discussed. Same assumptions are true as our atmospheric assumptions for the initial models. And so I want you to calculate what the expected temperature would be at the surface. And, I want you to walk through how you're doing it as if you're trying to show someone this is how you calculate this kind of stuff. So you'll probably draw diagrams, walk through. If you've got a whiteboard you can film yourself at, or draw on the screen, or draw on a piece of paper and show it, whatever you need to. I want you to be able to kind of teach how to do one of these basic climate models. So for most of you, that means I need you to do the black body one and to get to the basic climate modeling, because these ways of presenting kind of demonstrate to me and help you walk through that knowledge. You're going to have to learn it a lot more better, trying to create a little teaching video on it than you would if you're just like, oh, here's a quiz.
Sorry, teacher. I have a question.
Yes.
I submitted a bit late the petition about the indicators of climate change, and until now I didn't receive the grade or the response about it.
Okay,
So
I will. Sometimes when they come in late, I get to them a little bit later.
sorry, please. Not to indicate climate change. The first one about justifying science. The indicate is okay. So the first one, justifying science, when you give us, I didn't started the lectures yet. So
Okay, I'll go back and check it. I'll make sure you get that because that'll be helpful for future ones. Thanks for letting me know.
thanks.
Thanks, everyone. Have a great day. Have a great weekend. I'm off to a wedding. Now I'm going to Chicago with the family. That should be interesting. My niece is getting married, so that should be cool. But I'll be back on Monday and ready to go, and we can continue on with all the stuff that really affects climate change. I hope you guys are finding this interesting. Okay.
Yeah.
Okay, thanks a lot. Talk to you later. Bye-bye.
Thank you, Prof. Bye.